All right, hi, my name is Yoni Nazarathi. I'll be speaking about least squares for data science. This is a Jupyter notebook created using Julia 1.1. I will simply overview the main story and highlight what is in this notebook. So we start with a square matrix, with a rectangular matrix A, a 10 by 3 rectangular matrix A, and a vector B, and we would ideally like to find a solution to AX equals B. However, this system of equations is overdetermined. If we have a B which happens to be in the column space of A, then great, we can find such a solution X. So this X satisfies AX minus BT is indeed a bunch of zeros. However, in general, if we try to find a solution that, for example, satisfies the first three equations, then the first three equations are satisfied, but AX minus B won't be zero for the other equations. So we can't, in general, solve such systems of equations. What can we do? Well, we can try and minimize the error of AX minus B by minimizing the L2 norm, or just a norm, or alternatively the norm squared, the sum of squared. You get such a least squares optimal solution. It is not a solution to the system of equations, it is a solution to the optimization problem. You get such a solution using the backslash operator, A backslash B, and here it is. And then if you try to see what A times X hat minus B is, well, you don't get zeros, but it is guaranteed that this vector is minimal. The norm of that vector is 130, and we can't do better. Now, this code here goes around that point in R3, in three-dimensional space, around that point, and takes all kinds of random points around it and sees if we happen to do something better. And then would call this line 22 and would print found something better. But that's not the case. This line is never called. We never find something better. And if we look at the distribution of the losses, here's a kernel density estimate of it. Here it is. We can even use a little animation and create an animation to demonstrate this. So here we have x1, x2, x3. That central point in red is x hat with a loss of about 130. And when we start to take points around it and expand farther and farther, our loss just increases. Okay. So that is indeed the optimal point. This is not a proof, but a demonstration. One way to get this is via gradient descent. So you look at the loss function and you compute its gradient. This happens to be the matrix expression for its gradient. And then you run a gradient descent algorithm with learning rate eta. It's a gradient descent algorithm. So if you look at the trajectory of a gradient descent that starts at the point 1, 1, 1, and then just moves according to the direction opposite of the gradient, we end up very close to the optimal point. Okay. Now, the standard way of considering least squares problems is by thinking about the normal equations. These can be obtained in several ways. One way is by equating the gradient to zero and then getting these equations here. Okay, there they are, here, the normal equations. We can, of course, remove that too. Okay. The solution to the normal equations is x equals a dagger multiplied by b, where this a dagger is called the Moore-Poirot pseudo-inverse. It is A transpose A inverse times A transpose. Now the matrix A transpose A, also the Gram matrix of A, is non-singular if and only if A has linearly independent columns, as we have in that case. Okay. In this case, this is how we define the Moore-Poirot pseudo-inverse. Here's actually a Julia function that creates the pseudo-inverse, and here it is calculated by hand. You can see that these two pseudo-inverses are the same. This is a pseudo-inverse applied to the right-hand side B, and indeed we get our x hat. And similarly, this is just a solution of the normal equations using the backslash operator, in which case we also get x hat. Okay. Now, it is common to consider factorizations of the A for getting A dagger. Okay. So if you look at the QR factorization of A and do the following computation, then you see that A dagger, that the Moore-Poirot pseudo-inverse is a matrix R inverse times Q transposed. Now in the QR factorization, Q is a matrix with orthonormal columns and R is upper triangular. Okay, so in this case, X hat happens to be this. And here it is applied in Julia. We are actually using the QR factorization, putting in an F, getting Q, getting R. This is the upper triangular matrix R. This is a matrix Q transpose multiplied by Q, and we're getting the identity matrix, and the inverse of R times Q transpose times B, so that's a Moore-Poirot pseudo-inverse multiplied by B, gives us again the same X hat that we had. An alternative approach is using singular value decomposition, SVD, so A equals U sigma V transposed, and in this case, after some manipulation, we get that the pseudo-inverse, the Moore-Poirot pseudo-inverse, is V sigma inverse times U transposed. And here is a demonstration of how this works with SVD. So we compute the singular value decomposition. This is just a manual computation of the singular values, as they are the eigenvalues of A transpose A, and the non-zero eigenvalues of A transpose A, which are also the non-zero eigenvalues of AA transposed. Okay. After we do the square root of both of them, we get the singular values. So these are the singular values. You could see that each entry is indeed a singular value. This would hold also for any, if I change this index to 2 or to 3. Okay, and this was a pseudo-inverse that we got using the inbuilt function pinv, and here we're computing the pseudo-inverse manually using SVD, and you see that it's the same pseudo-inverse. So why do this? Well, there's several reasons. One thing you can do is ask what happens if A transpose A happens to be singular, because in the pseudo-inverse we had A transpose A inverse. Well, that inverse doesn't always exist. A transpose A will be singular if and only if A has columns that are not linearly independent, meaning linearly dependent columns. Okay, so this bit of code actually sweats a bit to find a matrix A that is of rank 2. Since we're getting matrices here with integer coefficients, this will happen after we sample enough random matrices. And indeed, from C204, we get this matrix A that has a rank of 2. Okay. You could see that the rank of A transpose A is no longer 3, and its determinant is 0, so A transpose A is singular. And yes, if you try to invert A transpose A, you get a singular expression. Still, you can solve a least squares problem, not the system of equations Ax equals B, but the minimization problem. You can do that. Here it is. And you can even compute the pseudo-inverse, right? And the pseudo-inverse times B is indeed this solution of that least squares problem. So let's now reproduce this using SVD. So if we do the SVD of the matrix A, singular value decomposition happens for every matrix A. And these are the singular values. These are the non-zero singular values. So R is actually the length of that matrix. So here, after we compute V times the sigma to the -1 times U transposed, where here we've taken V and U to be of column dimensions according to the rank, then guess what? We get the pseudo-inverse. You see, that's the pseudo-inverse, which is the same as the inbuilt pseudo-inverse. All right. So SVD works even when collinearity or holds, or in a linear algebraic sense, A has linearly independent columns. Now, we can also just start directly with the normal equations and apply SVD. Okay. So if you stick this in the normal equations, and you see that X solves the normal equations, and this derivation here takes the normal equations, represents A in terms of its SVD, and then obtains a pseudo-inverse in this manner. So this is really the, let's say, the quote correct way of obtaining the pseudo-inverse based on SVD, not this way that we showed before, because here we relied on A transpose A being non-singular. Okay, And it even happens that the singular value decomposition, so you see, when collinearity exists, or when A doesn't have linearly independent columns, and then A transpose A is singular, there are multiple solutions to the normal equations, but X happens to be the minimal solutions. Okay. All right. Now, an alternative way to handle such a case is by regularization. In this case, also called grid regression or Tikhonov regularization. And what we can do is we can add a term, the identity matrix, multiplied by the scalar lambda, where lambda is positive, to the matrix A transpose A. Okay. So, and that actually makes it non-singular because we've just added, it's not hard to show, right? So for any strictly positive lambda, the inverse of this thing exists, okay? And so does the pseudo-inverse. Now, what happens is if you take lambda very, very small, take the limit of lambda going to 0, you actually end up in the SVD-based pseudo-inverse. Okay, so here we see this. Here's a pseudo-inverse of A, the built-in, which is the SVD pseudo-inverse, subtracted by the regularized pseudo-inverse. Let lambda become smaller and smaller, and you see that the matrix norm difference of these two matrices goes to 0. Now, this actually appears as part of regularization, which is in general a machine learning and a statistical method of modifying the problem by adding this regularization term. So if you modify the least squares problem by adding the term lambda times the norm of x squared, you actually don't want your x's to be too big. Okay, you can represent the problem as follows, and this is actually a least squares problem where the new matrix A is a matrix A with these additional columns, rows added to it, and B is as follows. Okay, and hence the least squares solution is as follows. Okay, let's move on to some data fitting. So here are some quote reality situation. It's far from reality, but it is a situation where here's money invested versus long-term return, and it was generated as follows using this kind of model that has a linear term and a term to the power 1.8. Okay, so let's say we see this data and we decide to fit a curve of the form which is quadratic, beta 0 plus beta 1x plus beta 2x squared. Why do we do that? Well, we see a bit of a curvature and we say let's fit a quadratic model. Okay, how and why to choose a model is a different story. In this case, we can actually set the matrix A to be as follows. Now keep in mind, x's here are no longer the x's of ax equals b, but x's are actually data which become part of the matrix A. What we are seeking to choose now is a beta and minimize a beta minus y. Okay, so that's the best curve fit we can do. This is how we construct the matrix A based on the x values. Okay, and these are the beta estimates. Okay, here using the pseudo-inverse, here just using directly the backslash operator. And then the y estimator would just be the inner product of beta hat with 1x x cubed. Okay, and if we plot this over a grid, you see we fit this curve, and this is the least squares best fit curve for this data using this matrix A, which was a design choice. What about a different model? Okay, for example, what do we have in this model? So here we're going to fit a fourth order model. Okay, so we'll say, well, we want also 1x, x squared, x cubed, x fourth. We're going to fit a fourth order model. And we've now fit a fourth order model. So we see that there's a bit of bending in it, etc. Okay, it seems that with more complex models, we can perhaps fit slightly better. But of course, then comes the problem of overfitting. So what if we really take this to the extreme and take a complex model where we get powers x to the power 0, x to the power 0.1, x to the power 0.2, x to the power 0.3, up to x to the power 3. Okay. So for this, we do some fitting and we get these horribly big numbers and horribly small numbers. Okay. Something came out of this model and it looks perhaps like a good fit, but this is clearly a bad, crazy model. Right? It's composed of so many parameters, and I don't think it's better in any way. Well, then we can use regularization by choosing such a lambda term and then increasing lambda to shrink the parameters of this model and get a nicer model. And in this case, if we choose, for example, a regularization term of 2000, which is a big term, then we actually get a lot of coefficients to be very, very small, as opposed to these crazy big coefficients that we got in this model. In general, we've decided to fit this problem with a two-complex model, but this shows you how regularization works, and this is a regularized solution. In practice, how do you choose what lambda to use? Well, you might use a method such as cross-validation. There's also another method called lasso, which does regularization by actually knocking off variables completely. Here we've just reduced the value of coefficients or variables to almost zero. Okay, and there's also elasticness, which is a combination. Let's close off with a classification example. So we have here the MNIST dataset. Okay, so and we're just going to classify to distinguish between digits that are 3 and digits that are 8. So we get train 3 are all the images with labels 3, and train 8 are all the images with labels 8. We got 6,131, 5,851 of them correspondingly. Here's, for example, the 54th digit 3. Here is the 55th digit 3. Okay, and here is the 424th digit 3. Okay, and similarly for digits 8. Okay, here is the 22nd, 8th digit, etc. Or here is the first 8th digit. Okay, and we'll also keep the test images, so we're actually going to choose the MNIST test data set, of which there'll be like 1,010 3s and a bit less than 1,000 8s. Okay. Now what we're going to do for the y is we're going to put negative 1s for the 3s and positive 1 for the 8s. Positive 1 for the 8s. All right. So in total we have this number of data sets, and now what we're doing is we're creating our A matrix. So we have the first column is going to be 1s, okay, and that's for the beta 0 term, and then we have 784, that's pretty much here, pixels or numbers, and that's the 28 by 28, that's the size of each image. These are 28 by 28, so we splice it over 784 pixels. So this is our data matrix, okay? We can even do a heat map of this data matrix and see this is kind of all the data matrix together. It has the images spliced across. So now we're going to fit beta hat A minus Y vals, A backslash Y vals. This took a few seconds, okay, not too many. And we've got now beta hat, okay. We can actually look at the values of beta hat, and this is actually the classifier that we do. What does the classifier do? The classifier gets an image, and it does a beta hat transpose times 1, that was for beta 0, and here is the image. This vcat float on the image takes the columns of the image and makes a matrix from it. If that is greater than 0, it's going to say the digit is 8, otherwise it's going to do the digit of 3. Let's try it out on a few digits. So we try it out on the first 8, and we get an 8. We try it out on the first 3, and we get an 8. That's a mistake. We try it out on the second 3, and we get a 3. Let's even do one more. Let's try it on the third 3, and we get a 3. That's good. Let's do it on the fourth 3. We get a 3, so that seemed to be correct. We only had a mistake on the second one so far. Let's do it on the 8, on the second 8. We got an 8, okay? So there was, in these, there was just one mistake. Now mistakes can be of different form. You can get a true positive 8 or a true positive 3 or a false positive 3 or a false positive 8. And if we count how many, this is what we get. So this is a matrix where you get 968 corrects and 934 corrects. These are true positives, and these are the false positives, okay, of 3 or 8, okay. And this is the score matrix if you put it in this way. So it seems that we could use least squares to get about 95% accuracy, and that's without using any complicated methods. If you were to do a multi-class classifier using least squares on the digits 0, 9 in this way, you'd get about 86% accuracy with this data set and the corresponding train set. That's pretty much it. So I hope you can download this notebook and try using it yourself and enjoy. Okay, bye-bye.